some of these 14.2 questions that Haley brought up. The first one, number 4 in 14.2, find the average value of a function on that curve. Remember that a line integral is adding up a bunch of z values. And if we divide that sum by the length of the curve, that would give us the average z value. So very similar to Calc 1, if you wanted to figure out the average function value on this interval a to b, wouldn't you find the area and divide by the base to get the average height?
Yes, totally.
Totally, right? Obvious? If you want the average height of a function, you find the area beneath the curve, divide by the base, and that'll give you the average height. Same idea here. So the line integral, FDR, so this is going to add up all of the function values, and then we divide by the length of that interval, and that will give us the average function value on that interval. Oh, and I used the wrong notation because this is not, we're not integrating a vector field yet. This should just be FDS. Because we haven't, this is integrating a function, not a field. Integrating a function, not a field. So integral of FDS, that's going to sum up all the function values along the curve. And then if we divide by the length of that interval, we will get the average value of the function on that interval.
So it should be integral FDS over the length of the integral?
Yep, over the length of the interval. That will give us the average value. Second one, given the following force field, find the work required to move an object given the oriented curve right there. Say again?
It should be the same with the
So here we have a field, not a real value, not a function. So when we say function, we'll mean real valued function, so we don't have to say that every time. When we have a function, regular function that you never knew anything other than until this class. And then a vector field, so field and a function. With the last one, we're integrating a function. Now we're going to be integrating a field. So we're going to be doing this integral right there, integral of FDR. And to integrate FDR, we have to parameterize our curve. So this is on a curve. We have to parameterize the curve. So how are we going to parameterize this function on that interval? Say that once again.
let x equal t.
Let x equal t. So that's going to be our standard method of parameterizing a function. We let x equal t, then we let y be f of t. So that would be 3t squared. And then we have to come up with our domain. T is going to go from 0 to... So it's not a line segment this time. So when we do a parameterization of a line segment in the natural way, we always have an interval 0 to 1. But this interval, we're letting x and t be equal to each other. So we're going to go from 0 to 3. We also say to ourselves, okay, what t value gives us the initial point? Okay, 0. What t value gives us the terminal point? 3. So you can look at it in a couple of different ways. So now, this tells us that our line integral, which is, you'd be better off calling it a curve integral. We're going to integrate 0 to 3. And the way we evaluate FDR is by doing f dot r prime dt. So then we'll go into that.
Question.
Yes?
Does it matter what we choose for t here?
Bless
Like,
you.
let's say,
Thank you.
like, could we let t equal 3x squared if we wanted to?
Say that again. Let t be 3x squared. So let's put,
Yeah, so you could have just said y equals t.
you could have put the t here and then solved this for x. You could.
Does that still work?
Yeah.
Does it matter what you choose? No?
It does not matter how you, there's an infinite number of parameterizations for any curve. So it does not matter which parameterization you use. As long as you have the same initial point, same terminal point, it'll all come out in the wash. The natural parameterization of a function is just always going to be to do that, to put t in the x position and then f of t in the y position. That'll be the natural parameterization. Will?
Yeah, so you can choose. You can pretty much choose any parameterization you want. Although, if you want to avoid the professor making a mistake, you probably don't want to choose a very convoluted
Yeah,
parameter.
exactly. Yeah, choose the simplest.
Yeah. Make it easier on your professor.
Yeah,
Great.
make it easy on me. Keep it simple. So yeah, anytime you parameterize a function, I would just plug in a t there, but you can plug in anything you want and make it more complicated.
What number is this one?
This is number 7 in the homework.
Awesome.
And let's take a look at the next one. So this is number 8 in the homework. Given a field, find the work required to move an object between 2 points. So here, they don't give us a curve to move along. They just tell us to go from that point to that point along a line segment. So we have to generate the parameterization ourselves. So parameterizing a line segment.
Isn't it already parameterized by default? Or
Uh,
at least like the force field looks like it is.
So, well, the field is the field. That's different than the curve that we're going to parameterize. So the field is defined on the curve.
Okay.
So in this case, the curve is just a line segment. But we need to come up with the parameterization of the line segment. And then that field will be defined at every point along our line segment.
Okay.
So the natural parameterization, again, there's an infinite number, but the natural one is to use this as the starting point to get the displacement between the two multiplied by t. So let's do that. So we're going to have 3, 1, 4, that's the starting point, plus the displacement vector. Looks like it's going to be 3, 1, 4. Oh, that's weird. 3, 1, 4 times t. And whenever we do this natural parameterization of a line segment, the domain is always
0, 1.
0, 1. If you plug in 0 for t here, you're at the start point. You plug in 1, and you're at the finish point.
I have a question.
So that's our parameterization. Yeah?
Should that first one be a point and not in angle brackets?
No, it's the vector. So this is the initial vector, which points to the initial point.
From like the
So-
origin?
Yes.
Okay.
So that's going to be a standard. That's going to be a vector in standard position that points to that initial point. So the idea is that we have 2 points somewhere in 3-dimensional space. We've got our coordinate system, and we're just going to point to this is going to be our r sub 0, and then we go along this line that way. That's going to be, if we were to label these things, this vector is r sub 0, this vector is v, where we did terminal point minus initial point. And then the effect of that when we put the t in there is that we're going to get all possible scalar multiplications of v. So t is going to be what gives us the entire line. So if we just did r naught, we would get to that point. If we did r naught plus v, we would get to that point. But if we want all the points on that line, we do r naught plus tv. And that will give us small. Oh, yeah. And now that we have our parameterization, we're good to go. Now that we have our parameterization, the integral that we're looking for, the integral is the integral of FDR along the curve. So now we're going to integrate, we're going to plug in f here. We're going to take the derivative. What's the derivative over here? 314. That goes in there. This is a dt. We parameterize it on the interval 0 to 1. So we do that kind of thing.
Is that not magnitude?
Say that, no, it's not magnitude, because this is a vector, so that has to be a vector. Right? The field is a vector. Field is a vector, so this is a vector.
okay.
So let's go back to the very first one. Here, our evaluation along this curve This one, we have to use magnitude because this is a function, so this has to be a function. Right? Yeah?
Can't you take the magnitude of a vector and still get a vector back?
No.
No. Okay, that was.
So magnitude of a vector is always, it's a function. You can get a real valued function.
Okay.
You can get a function, but not another vector.
Like with t's left in it and stuff.
Yes.
That's the, okay.
So you can get, so the magnitude of a vector is a function in general.
Okay.
A scalar valued function. The magnitude of a vector, like if we take a look at something simple, like if we have this vector t comma t squared, the magnitude of this vector, and I didn't take the, well, let's just take the derivative anyway. So the derivative is going to be the magnitude of this, and that's a function. So the magnitude of r prime is going to be the square root of 4t squared plus 1. So the magnitude of a vector is a function in general.
Exact problems on the first place.
And so we just have to make sure that our types line up. If this is a function, this has to be a function. If this is a field, that has to, or if this is a vector, then this has to be a vector. It's always going to be r prime, then you just have to decide, is it the length of r prime, or is it just r prime? And it's just r prime if you're integrating a field, it's just r prime. If you're integrating a function, it's the magnitude of r prime. So in this case, the way you should be thinking conceptually about this is that you're adding up all of the tangential components of the vector field along the curve. So if you're imagining, in this case, it's a simple curve, it's just a segment. The vector field, what you should be visualizing is just a bunch of little arrows coming off this thing. There. Just a bunch of, and that's obviously, I'm just drawing random vectors. That is not that vector field. Those are not representative vectors from that vector field. But each one of this is the concept that you should be thinking. The integral of FDR, which we also wrote initially as the integral of f dot TDS. So these are equal. If we integrate it, we could also call it f dot TDS. Same thing. This is adding up all the tangential components of the vector field. So if we look here, the tangential components are all these little guys that are parallel to the curve. So that integral is adding up all of those red vectors. Whereas the other integral that we learned last time was adding up all of the perpendicular components. So each one of these vectors has a component that's perpendicular and a component that is parallel. So f dot capital T adds up all the tangential ones. F dot n adds up all the perpendicular ones. So one of them is called, in general, we call it circulation if it's a closed curve. If it's not a closed curve, usually they just call it work. Integral of FDR is work. The other one we always refer to as flux. So f dot n is flux, f dot t is circulation.
So how do you start this problem? Like, I don't even know what to do with that whole force field, like that whole thing up there.
That thing?
Yeah.
is that kosher?
Like, what do you do? Like, do you actually just
That is so kosher.
just throw it into the integral?
You can
or
have it for lunch.
What do you do with that?
So you dot it
Into what? Into that?
into this. So you dot it with r prime. So here you can proceed in one of two ways.
Okay.
So this part right here is a scalar function down in the denominator.
Yeah.
You can imagine that in each denominator if you want, or you could leave it outside of the dot product. It doesn't matter which way you go. This one, you can think of combining these into one vector. So this is one vector right there. You take the derivative. So the derivative in this case is that. So that's here, so you dot this together. You have to take your x, plug it in here, your y, plug it in for y, your z, plug it in for z, so that you have just t's, and then dot those two together.
Did you do the same in the denominator?
So the denominator, x squared plus y squared plus z squared, is going to be that squared plus that squared plus that squared. Right, so then you're going to have just t's. In all cases, whether you're doing a function or a field, the idea is that you're going to collapse your integrand to just t. Should just have t's in it. So if you're confused at all, there's two things that you should be thinking of. Vector and vector, or function and function. And then the next step is turn everything to t. Everything should be turned into a t. So the way you turn a field or a function or a vector, a derivative vector, the way you turn it into t's is to go to your parameterization of your curve. So everything depends on your parameterization.
So pretty much in this case, whatever we see x, whether it's in the up there or in the denominator, we just replace it with 3 plus 3t?
Yes.
Okay.
So your parameterization is everything. That is the key. That's the linchpin to everything. If we parameterize it this way, then all x's are this. All y's are that, all z's are that. If you used a different parameterization, then your x's, y's, and z's are different. But then your t, your limits are also different. Instead of 0 to 1, you might have some other limits of integration.
And so you're saying take that top vector and then dot it with this vector that we found, and then you can put that like 1 over back in afterwards, like the 1 over x squared, y squared, z squared.
Right. So you could do the dot product of those two. So you get 3x plus y plus 4z,
Yep.
and then replace the x, y, and z.
Yep.
And then this thing down here, and then you have a big fraction.
And then just put it over it and
Yeah.
then solve that. Okay.
Mm-hmm. Yep. Omar?
Does dot product change the order of operation? Where does dot product land within PEMDAS?
There's no order of operations that changes, because when we do the dot product, we go
Right.
right,
I
x
think-
times x, y times y, z times z.
So dot products does supersede division-ish, kind of, not really.
It's like
Um,
multiplication, right?
The PEMDAS stuff just is still there. Like a dot product is just multiplication.
And addition.
And multiplication and division can go in either order.
Right.
So you could divide this into each component and then dot,
Or
and then
dot.
add,
Okay.
or you could dot and then divide once. Yeah. So it will work out fine if you treat dot as multiplication.
It'll come out in the wash.
Come out in the wash.
Is that your new favorite phrase?
No.
Okay.
I've got lots of other favorite phrases.
So, whatever.
Some of them I shouldn't say in this class.
Yeah.
Okay, so let's go to this last one, number 11. So same idea here. We've got a function. We've got a curve. So should we be doing, are we dealing with functions or fields in this case? Functions or vectors? Yeah, functions. We're dealing with functions. So that's not a vector field, so we're not going to try to do vector times vector. We're going to do function times function. So when we find a parameterization of this curve going from the origin up to 1, 1, that will be the natural parameterization. The natural parameterization will be t comma t squared, and what would be the interval for t?
0 to 1.
Yeah, 0 to 1. Right, that's the natural parameterization. You plug in 0, you're starting here, you end up there. So now they're saying, what about if you go in the opposite direction? Opposite direction. So we have to try to come up with a way to reverse the orientation.
1 to 0.
I don't know, check. If you did integrate from 1 to 0, if you plug in 1, yeah, that would work. That's true, that would work.
Yeah.
You wouldn't write your interval like this, though. You don't write an interval with backwards, you know.
Yeah.
There has to be an increasing relationship between the left and the right endpoint. Is there other ways to parameterize this differently so that, is there a way we could parameterize it differently so that we still are on the interval 0 to 1?
Multiply by negative 1.
Flip them and then just change the sign.
So someone said multiply by -1. Okay, let's try. All you can do is try. So if you multiply by -1, that's not going to work because when you plug in a 1, you're going to get -1, -1. So that won't work. We heard of flipping them. Sometimes this is enough to work. Let's check. Plug in 0, you're at 0, 0. Oops, that's not working then. So somehow we have to
Don't you want to beat it? 0, 0?
say again.
Isn't that what you want?
No, you want to be at 1.
We want to be at. We're going to start. We want to start there,
Gotcha.
right?
add one?
Can you add one?
Let's try. And there's not one thing. Add one to both.
Yeah.
So if we put in 0 there,
Then
oh,
we'd
we're
add
not.
4.
We plug in 0, we're 0's fine.
yeah, we're at
But
1.
when we plug in 1, we're not fine.
Do 1 minus 2.
Boom!
What? What did he say?
That's it.
And then he said no.
That's it. That's it. So if we parameterize it like that, if we replace all t's with 1 minus t, that will work. And then the question to you is, all right, let's just check first. Plug in 0, we're at 1, 1. Plug in 1, we're at 0, 0. So what if the interval went from 0 to 4? What would we replace t with?
0 minus 4 minus 2.
So if t went from 0 to 4, we're going to take the t's and replace them with 4 minus t.
That makes sense.
Right, that just bounces us to the other side of the end of the interval.
Oh, wow.
Right?
Is this like this? Is this like a?
What?
Well, I mean, you can't really call it a law because it's not going to work everywhere. Is it like a theorem? Is this like a essential?
When
thing
your
that
interval
works
starts
that way?
at 0 and ends at some other point, this will always work. This will always work.
So it always works when.
It always works in some cases.
Okay, in some cases it always works.
Nico.
So, does that mean it would also work if instead of having the 1 minus t in parentheses, you had 1 minus t squared instead of?
Let's check. I don't think that will work because we have to make sure that our coordinates still maintain this relationship. And so if you did what you suggested, and we had 1 minus t and 1 minus t squared, we might be there and we might be there, but the relationship between x and y would not be that y is equal to x squared anymore.
Right.
Then it would be y equals, something different. So it's not going to match the same curve. And sometimes that doesn't matter. We're going to see very shortly that if our force field is a conservative field, it doesn't matter how you get from point A to point B, the integral will be the same. So we'll see that very shortly.
So what if you're not going from 0 to 1? Is there a method to do this without all this trial and error bullshit?
Oh, buddy.
Whoa!
I hate trial and error.
Slow down, Trixie!
That
We're not going to see a lot of this. This is just
Okay.
like just a little subtlety that if you wanted to go backwards on a curve that started at 0, 0. Yeah, we're not going to see a lot of this. This is not a fundamental component to what we're about to do.
Okay.
It's just a little interesting side note on reparameterizing things. Okay, compare the results. What do you think the difference is going to be? Your first suggestion tells you what the answer is. What's the difference going to be? Yes, -1. Because your first suggestion was, can you just do this? And if you take the limits of integration and you just swap them, you get the same result, except you're multiplying by -1. Right? And so it's just like work integrals if you've taken physics. If you integrate one direction and you get positive work, you go the other direction, you get negative work. So it's just going to change it by a factor of -1. So if you change the orientation, you change the value by -1. That's all that happens. Oh, conservative vector fields. Conservation of energy. Conservation of energy. Whatever that means, kinetic energy plus potential energy is the total energy, and that's the same if you're in a conservative field at point A and point B.
U initial plus K initial equals U final plus K final?
Yeah, something like that. Ish.
Yeah, I just
Just do that this week?
Yeah, I did that actually this morning.
Oh, excellent.
You also need a U in there somewhere.
Excellent.
U's?
Okay, so first, couple of simple definitions.
Yeah, U1, K1.
Yes. This is a closed, simple curve. This is not closed, but it's simple.
Oh, God.
Oh, no.
A curve that's not simple is one that intersects itself, and a curve that's not closed is
Not
a
close.
curve where the terminal point and the initial point are different. So this one is closed, it's a loop, but it's not simple because it's self-intersecting.
Okay.
99% of the time, we want to be dealing with this situation. We want it to be simple, so it's not self-intersecting. We want it to be closed, so that we can talk about an inside and an outside and an orientation. So that's 99% of our situations will be like that. We'll have a simple closed curve as the boundary.
Will we ever deal with the not simple ones?
We may be dealing with not closed, but we're not going to really be dealing with not simple.
Okay, because
Alright, we're getting to the question.
It's the same like in knot theory when they talk about like simple knots and not simple knots. It's the same thing.
It's the same idea with knot theory. Exactly.
because these intersecting lines are from what I see are kind of the bane of mathematics.
Yeah, when you have something like that, that can be a problem in general. But remember that we parameterize, so that's a little different. So
Use Jacobian.
So curves that are intersecting, if you parameterize it, you would look at that and you might say that's not a function of x. Now if you do this kind of thing, not a function of x. But you could write it as a function of t, right? Yes. You could have t equals 0 corresponding right there. And as you're trucking along, even though it's self-intersecting, you can have an initial point of t and a terminal point of t, and you could write it as a vector function, even if the curve intersects itself. So these self-intersecting curves aren't necessarily, a total pitta. But they.
What is this?
But we usually don't deal with that. So let's talk about shapes. And similar type of thing. This idea between simple and connected. So this shape right here is the best. It's connected and it's simply connected. Simply connected just means any loop can be shrunk down to a point that's contained within the region. So here we can't shrink down this loop over here because we've got this missing section in the middle. So that's not simple. These are both connected regions. You can get from wherever you draw point A or point B, you can get to, if you draw that and that, you can come up with a curve that gets from one point to the other. So they're both connected. Regions that are not connected have some break in them. So these are not connected. But this is simply connected. If you draw a closed loop in here, you can shrink it down to a point. Over here, it's not connected, obviously, and it's not simple because you take that loop and you can't shrink it to a point.
So pretty much, if it's be connected, there has to be at least one path from any one spot to any other spot
For it to be connected.
So if we take those two not connected ones, and then actually just add
build a
line.
bridge?
Yeah, add a line in between them. So if you take one on one end of the line and a point on the other end of the line, there is exactly one path in between.
Yeah. So if you connect them like that, then that is a connected region. Yeah.
Even though there's like one
path only between the two.
Yeah.
Are there Clopen curves?
No.
I don't think guys really
Not yet.
understand.
You could invent them.
I think the ones with the intersection in the middle should be called Clopen because it's both closed
No.
and
Oh
open.
no, don't even.
I don't think this class fully understands cloping very well.
Yeah, we
Concept
better not
of
go
cloping.
there. You'll learn that in a couple years.
A couple? Where
All
does
right.
it come up?
Clopin?
Yeah.
Graduate math classes. Okay, more than a couple years.
Ouch. Thanks.
I know, well,
Getting
graduate,
roasted
you
here
have
in
to finish a
town
bachelor's degree in math before you get to graduate school in math. So that's more than a couple years. Clopin is a ways off.
Okay.
Although you might do it in a bachelor's degree if you do a class called advanced calculus. You may deal with Clopin stuff.
There's another calculus after Calc 3 called
Yeah.
advanced calculus?
Yeah, analysis.
Which is also known as analysis. So there's usually analysis 1, analysis 2, real analysis 1, real analysis 2. And those two courses go back through all of Calc 1 through Calc 3 and prove every single theorem.
Hell no.
Why? Analysis is all about proofs. And so that class is a hard class.
Everyone's like, no, and I'm like, yeah.
There's one in every group.
That sounds horrible.
Yeah, it's a hard class. Okay, so vector field is said to be conservative. If this stuff here is true, I'm going to back up one slide and insert a definition from 14.5. And I don't know why the book does this in 14.5 and not right now, because it's much easier for us to talk about conservative vector fields if we know what the curl of a vector field is. And so what we're going to do is define the curl of a vector field. Curl is going to be another vector field, another vector. And the way we find it is like this. We're going to put I, j, and k at the top. And then we're going to put partial derivatives in the middle row, the partial with respect to x, y, and then z. And then we're going to put the components of our vector field down in the bottom row. So our vector field is built up of 3 functions, f, g, and h. And that vector field is going to be called the curl. And the curl is going to give us an indication of circular motion within our vector field. It's going to measure, and I should put a vector symbol above this f. So the curl of a vector field is another vector field, and it's going to be an indicator of rotational motion. Here's how we evaluate this. The curl, we always expand about the top row, and we put the standard plus, minus, plus business up there. Now, the middle row is just partial derivative operators. Right, this says the partial with respect to x, partial with respect to y. So when we go to fill in the blanks over here, we are going to do the I first. We cross out this, we cross out that. So this is going to be interpreted as the partial of h with respect to y minus the partial of g with respect to x. So this is going to be h sub y minus g sub x, if we use our abbreviated notation.
Sub z?
Did I say it wrong?
Yeah, you said
x.
sub x.
Oh, yeah, z. Thank you. Yep.
Is this pretty much just crossing the gradient with the function itself, with the vector itself?
Yeah. Uh-huh. Yeah, because it's almost that. It's almost. Yeah, it's not quite, because this is the gradient. It's not quite the gradient, right? The gradient is f sub x, f sub y, f sub z. So it's not quite the gradient, but it's very close. Okay, so then the middle component, we cross out the top row in the middle, and we go backwards. So it's f sub z minus h sub x.
Oh, I see. Like gradient is taken from a function on a
Yes.
vector, right?
And then the last one, which is going to be the most important one that we will see a bunch, it's going to be g sub x minus f sub y. So that's the curl. All right, we just crisscross all these things, and we get this thing's called the curl. All right.
F sub z minus h sub x, not the other way around?
For the middle?
Yeah.
So for the middle, we cross h sub x minus f sub z, but then we switch it because of the minus that sine array, the sine array value. So definition, f is conservative if and only if curl of f is 0. So a conservative vector field has no curl. If you have no curl, conservative vector field. So a conservative vector field is a field that doesn't have any rotational activity going on. It's got to be one of those radial type fields. So conservative vector field, did I say that backwards? No, I said that right. Yeah, there's no rotational stuff going on. There's no curl. The curl is 0. So a radial field has no curl. So conservative field has no curl. So if you decide that your vector field has no curl, you know it's conservative, and then you can make all of these things, all of these assumptions, and all of these theorems are going to fall right into place. Now, look at what they did here. They say the test for a conservative vector field is this, this, this. No one in their right mind can remember those equations. It's so much easier. But those equations, if we go back, that's the first one, that's the second one, that's the third one. So the way those 3 equations come to be is by looking at the curl. It's way easier to understand how to do a determinant. You do the determinant, and if you don't get 0, 0, 0, then you don't have a conservative field. If you get 0, 0, 0, then you have a conservative field. Now, when we're dealing with 2 dimensions, this is the only component that is going to matter because those two are automatically going to both be 0 if you're in 2-dimensional space. In 2-dimensional space, you can think of a conservative field as one where G sub x equals f sub y. G sub x equals f sub y.
Yeah, because pretty much when you're taking cross product of a two-dimensional vectors, you just kind of add on.
Because it's going to point straight up.
Yeah.
Right? When you do the cross product of 2 vectors in the xy plane, it's going to point straight up no matter what, or down. So you're going to have 0, 0 no matter what. Yep.
So with the conservative fields, can they be conservative in some parts and then not in others? It's just all.
Because you've got your field. We never talk about piecewise defined fields. Your field is your field, and it's creating arrows, however it's creating arrows, either in a conservative way or a non-conservative way.
Can you go back for 1 second?
Yeah. Okay, so if you're going to memorize anything, this is the one to memorize for 2-dimensional space. I'll give you another reason why and how to memorize that. Basically, it's just a crisscross, though, because you're saying that G sub x is equal to f sub y. So let's just write that out. So if f is just 2-dimensional, f comma g, then f is conservative if and only if f sub y is equal to g sub x. So you just crisscross them. You take the first one and partial it with the second variable. Take the second one and partial it with the first variable. You get gx equals fy. All right. So that's what this is. Again, no point in trying to memorize those formulas. This one is the most important one for 2 dimensions. So here's what we would do. So here we have 2 dimensions. This is f comma g. So we just want to do the crisscross. We want to do f sub y and g sub x and see if those are equal. And if they're equal, then it's a conservative field. Now, one other thing. Let me go back up here for a second. So one other thing. Remember, we talked a little bit about this the other day, is that if we have a function, phi, and we take its gradient, that builds a field. Right? And you can always do that. If you have a function, you can always take the vector of partial derivatives, which is the gradient, and you have a field. The question that we want to answer is, if you're provided a field, is there a phi that has gradient equal to that field? If there is, then phi is called a potential function. So we're going to look at random fields and decide, hey, does this come from a phi or does it not? And if it's a conservative field, there will be a phi. If there's not a conservative field, there's not going to be a phi with gradient field equal to the field.
Are we going to be given a phi, or sorry, given some vector field and have to work backwards to find some phi?
Yep.
Okay.
Yep, very shortly.
Okay.
We will do that very shortly. So the only way you even want to look for phi is if you know it exists. And the only way it will exist is if the field is conservative. So you take the curl, and if the curl is 0, you know phi exists, and then you go try to find it. All right,
so pretty much, yeah, curl of 0 always means phi exists. There's a phi.
Yes.
And
curl being 0 means there's always a phi.
And phi will only exist if the curl is 0.
Say that once again?
Yeah, so pretty much there isn't going to be phi that generates a field where the curl is not 0, right?
Say that once again?
So you have... Is there any way phi will generate a field that is not conservative? Or not?
No. So if you have phi, it creates a gradient field, and that gradient field is automatically conservative because you built it from phi.
Okay.
So if you start with phi and you build the gradient field, that gradient field is the gradient field for phi.
Okay.
So that means it's got a phi. If you start with phi, you end with phi. But if you start with capital F, you don't necessarily have a phi.
All right. Yeah, there's a term that would have made that easier, except that one implies the other all the time, and vice versa. I forget the name of that. That sort of relationship.
Yeah. One of those things.
Only that work with pi. Start with pi.
Is this conservative or not conservative?
Conservative.
So because these are equal, so f sub y is equal to g sub x, that implies that f is conservative. So that means phi exists.
We're not finding that yet, though.
Oh, yes, we are.
Oh, it does say.
So this tells us then that capital F has this going on. That means there is a phi where this is phi sub x and that's phi sub y. Right? That's how you would find the gradient of phi. You would do phi sub x comma phi sub y. Now, one quick observation. Isn't the partial of f with respect to y, isn't that phi sub xy? And isn't g sub x really phi sub yx?
No.
And those are mixed partials and they're equal. So a conservative vector field is one in which the mixed partials are equal. So let's go through this carefully. So if f is conservative, then the first component is called phi sub x. The second component is called phi sub y. Our test is to take the partial of the first one with respect to y and set it equal to the partial of the second one with respect to x. So really embedded underneath is the way that we know a field is conservative is, the way we know that, the way we know a field is conservative is that these mixed partials are equal.
So you're naming the x value phi sub x, not taking the derivative with respect to x of phi.
Mm-hmm.
Okay.
Yep. So if this is we're trying to figure out whether this is a gradient field for phi. If this is a gradient field, if it's a gradient field, then that's phi x and phi y. We don't know if it's a gradient field or not, so that's why they use f and g. Because we don't know. We don't know if there's a phi. It's only going to have a phi if it's a conservative field, so we need to have a more general way to talk about the components of the field. So we call the components of the field f and g. But if the field happens to be conservative, then little f is phi sub x, and little g is phi sub y. So phi will have second mixed partials being equal.
Okay, I think you just said this, but f sub y is equal to phi sub xy.
Yes,
But
exactly.
not f. F is equal to that in the red over there. But that's only because we figured out that it's a conservative field.
Yep.
So it's always that way if it's a conservative field.
Yes.
You can just replace f and g with phi. As soon as we
Replace
realize-
f and g with phi sub x and phi sub y.
All right.
Yes.
Okay.
Yes. Yes. Exactly. These conservative fields. Okay, so now we have to find another question.
So,
This is so exciting. This is what teachers live for.
so because you've got some mixed partials over there equal to each other, does that mean that this is really just some kind of adaptation of the second partials test, or?
This means back when we were first studying functions of multiple variables, we said that if a function, what did we say? We said that a function is, I can't even remember the definition. We had some definition that the mixed partials had to be equal. And I'm forgetting exactly what we had.
For like critical points? Or what?
It wasn't second partials test though. It was before that we said that I can't remember now. Because we didn't do much of it. It was more of an observation that if we had a continuous function, the mixed partials were always equal.
Huh.
So if the mixed partials are always equal, I don't know what you say going the other direction. But if we have a continuous function, which is going to be phi, the mixed partials will always be equal. If we have a continuous function.
Gotcha.
But I think it's more than that. I think it's a differentiable function.
Diana found
If
it.
it's twice differentiable, the mixed partials will always be equal. I think is what it was. All right, so now we have to do the hard part.
Yay.
We have to find phi. Now we know it exists. We figured, now we know it is there. We know it exists because these are equal. So now we have to find it. So here is how we find it. This is the hard part. And with 2 dimensions, it's a lot easier than with 3. So let's make sure we understand 2 dimensions. Because if we don't understand 2 dimensions, we will not understand 3. So phi sub x, that's the first one, first component. And phi sub y is the second component. So we write down this system. And there's multiple ways you can do this. But we're just finding an antiderivative. Right? We're trying to build phi from its derivatives. Right? We're trying to build back up and figure out what phi is. That is exactly what taking an antiderivative does. Right? If I say the derivative of something is 2x, then you integrate it to get whatever that function was. So that's what we're doing. The only difference here is that we have 2 partial derivatives. So we're going to take one of them and partially build back phi, and then we're going to partially differentiate that and set these 2 things equal to each other and then go back up. So we're going to start at a partial, go up to phi, go down to the other partial, and then go back up to phi. So there's going to be this process of we start at phi, and normally if we can, we start at phi sub x. So what do? We integrate. If we want to integrate this, we have to integrate with respect to x. Right? If we have phi sub x and we want to get to phi, we integrate with respect to x. Because the way we got to phi sub x is to differentiate with respect to x. So now we have to integrate with respect to x. So that's going to give us x to the 4 divided by 2. Plus integrating this with respect to x, we're going to get x squared y squared over 2 plus okay. And that c is a function of y. Okay, so let's understand that very carefully. Why is that a function of y? Think about partialing with respect to x. If this had y squared in it, what's the partial of y squared with respect to x? 0. If this had sine of y plus tangent of y plus y cubed, the partial of that with respect to x? 0. So there can be y's in this constant of integration.
No x's.
No x's though, because we partially integrated with respect to x. So we've recovered all of the x's. We've recovered the x's, but the y's are only partially recovered because there could be some in that constant. Now we partially differentiate that with respect to y. So if we partially differentiate with respect to y, that first term goes away. Partial of the middle with respect to y, the 2's go away, so we get x squared y. And the partial derivative of c with respect to y, that's just the derivative because there's only one letter in it. Right? That constant is a function of only y, so its partial is really its derivative. It's just c prime of y. Right? Now we have 2 expressions for phi sub y. So we resolve by setting them equal to each other. We're going to resolve that constant by setting these 2 equal to each other. So when we set those 2 equal to each other, we get 2y cubed plus x squared y equals x squared y plus c prime of y. That goes away. That tells us that c prime of y is equal to 2y cubed. Now we can figure out what c of y is. If we want to get c of y, that's just a regular old antiderivative of 2y to the 4th. So that, or excuse me, of 2y cubed. So that's going to be y to the 4th divided by the 4. The 2 cancel, so we get y to the 4th divided by 2. Plus a numerical constant. And I am going to always use a k just to distinguish. When we know it's a numerical constant, I'll put a k. And if it's a constant that's not numerical, I'll put c of y, c of x, whatever it is. But instead of just a c, just to make it clear that that's a number, that there's no y's or x's in that thing, I'll just use a k. Now we have completely recovered phi. Phi is now equal to x to the 4th divided by 2 plus x squared y squared divided by 2 plus y to the 4th divided by 2 plus k. So there is our family of potential functions. So if it asks for just one potential function, you can let k be 0. This is a family of potential functions. Just like an antiderivative, when you integrate something, you get a whole family of antiderivatives, right, depending on what the k is, or the c. So here we have this is a whole bunch of surfaces, and every one of those surfaces, regardless of k, is going to have that gradient field. All right.
Doing this problem reminds me of trying to fix something that was broken a long time ago. Just trying to recover it.
Yeah. Trying to fix something that was broken a long time ago.
Quick question.
Yeah. Question?
So you said that we were doing it with the phi with respect to x first. Why is there why?
There's no difference. You could start here and start recovering by doing integrate this to get phi,
Yeah.
take the partial of that with respect to x, set those to equal, and resolve the constant that way.
Sometimes it just might be easier to do one.
Yeah. I mean, a lot of times, I just will always start with phi sub x unless there seems to be a noticeable difference. Usually it's about the same.
So we never jump from doing phi sub, or I guess integrating phi sub x and then integrating phi sub
You
y.
could. That's another way.
Okay.
You could do partial integration of this with respect to x, partial integration of this with respect to y, and then try to resolve that way too.
Okay.
That is also a possibility. That is also a possibility. So we have 3 different options here. Phi sub x first, phi sub y first, or do them both. 3 options. Now when we get into 3 dimensions, there's going to be a whole bunch of options.
Are there times where one option is better than the other, or do they both work the same?
Most of the time, either one is going to work. In order for one to be so much more difficult than the other, you'd have to have a pretty concocted function.
You just have to remember, if we do the second way, add k at the end.
Yes. Yeah. So in all 3 cases, we're going to have a k at the end. Unless, again, if this homework says find a potential function, then you could pick k to be 0. But in general, potential function is a whole family of functions. Family of surfaces. All right. Well, 3 dimensions. So this is funny because they put the 3-dimensional one here, but we have one more example of a 2-dimensional one. So I'm going to scroll down here and let's do the 2-dimensional one, and then we'll go up and figure out what the heck they mean by the 3-dimensional one. So this one is not crazy. So we have to first decide if it's conservative or not conservative. So it's conservative if it has no curl. And in 2-dimensional space, that boils all the way down to crisscrossing here. So right now, that's f, so we want to take the partial of the first component with respect to y, and the partial of the second component, that's g, with respect to x. All right, those are equal. So f sub y is equal to g sub x. So that implies conservative field. That implies that f can then be rewritten. You can think of it as phi sub x comma phi sub y, because it's conservative. If it's not a conservative field, you would never introduce phi. So let's start from scratch. We will say that phi sub x is equal to minus y. We're going to say phi sub y is equal to minus x. And we'll start up here at the top. We're going to partially integrate with respect to x to recover what phi looks like. So integrate with respect to x. That means we're holding y constant, so the constant is a function of y when we do that partial integration. So we get c of y. Then we come down, we're going to find phi sub y. That's minus x plus c prime of y. Now this one's pretty straightforward. We set those equal to each other. We have phi sub y, phi sub y. So we're going to set this equal to that. So we have negative x is equal to negative x plus c prime of y. This tells us that c prime of y is 0. This tells us that c of y is just a numerical constant. Yeah?
Will you remind me real quick why it's C prime once you take the...
So if we're differentiating,
Yeah.
but we're partially differentiating with respect to y, this has two variables, so you can only partially differentiate. This only has one. So the partial derivative with respect to y of a function of y is the same thing as the regular derivative with respect to y. So a partial derivative of a one variable function is really just the regular derivative.
Are we integrating them?
No, we're differentiating to go from phi to phi sub y. So we integrate here, then we partially differentiate here, and then we go back to here.
Holy, all right.
Right?
Okay.
You see the path?
I see it.
So we start down at a partial derivative, go up to the function, come down to the other partial derivative, and then resolve the two. All right, so that tells us, in closing, that phi is equal to negative xy plus the constant that we just found. So that is going to be our family of potential functions.
Pretty much.
All right. Okay, so to do 3, do that. All right, here we go. Trying to read that, you will not understand it. You will only understand it if we start to do one, and then we can go back up and sort of talk about why they say it the way they say it. Trying to read through that ahead of time is going to be so hard.
Is that option of integrating the x and y and the z separately,
That's a possibility. Yep. You could integrate with respect to x, y, and z, and then start resolving constants. Definitely. First, let's decide if it's conservative or not. So this is 3 dimensions, so we'll find the curl. So the curl we will find by evaluating this determinant. So top row is the vectors of length 1 in the coordinate directions. And then we put our partial with respect to x here, partial with respect to y, partial with respect to z, and then our f, g, and h. So that's the curl setup. This is a vector. The first component of the vector, partial of 1 with respect to y, 0, minus the partial of x with respect to z, 0. Second component, partial of y with respect to z, 0, minus partial of 1 with respect to x, 0. Third component, partial of this with respect to x, that's 1, minus partial of y with respect to y is 1. So that is the 0 vector. Therefore, the field is conservative. So this implies f is conservative. So that implies that we can do the following.
Wait.
Yeah,
If you take
waiting.
your x component, the partial y, or partial 1 with respect to y is 0. Partial is... Oh, never mind. You're right. Keep going.
Carry on.
Scary. Okay. So, Eric suggested one option, which is to integrate all 3 of these. That is one possibility. You can start with x, you can start with y, you can start with z, and you can go a meandering through all of these partials to get back to phi. So our big goal is to figure out what phi is. We want to recover phi. So I'll go this way. I'll always start with phi sub x. Here we go. So partially integrate integrate phi sub x with respect to x. So this is going to give us phi equals x y plus constant of yz. Okay. Because if this has y's and z's in it, and we partial this with respect to x, all those would just disappear. So it can have y's, it can have z's, and it can have constants. All right. So then we're going to come down, partial it with respect to y. Partial with respect to y. And this is going to be c sub, this has two variables in it, so it's only a partial derivative, right?
Can you
Yeah.
explain?
You check partial derivative of z, you get 0, right? So we see y is with y 0.
Wait, say that again?
You take the partial derivative of z with respect to y, you get y 0, right?
Partialing this with respect to y, we're going to get x,
The constant. Yeah.
but we don't know how many y's are in here. There's y's in here, there's z's in here, there's constants in here. So if we take the derivative of this with respect to y, that's the partial with respect to y. Right?
Yeah, because I think z should replace by 0. Because z.
No, what about if you tell me this? If you have something like, if you have y squared z cubed, and you partial this with respect to y, don't you end up with some z's still? Right? There's still z's in there. I agree that if it was y squared plus z squared, you could say, oh yeah, the z's are all gone. But if there's a z multiplied by a y, then it's going to still, this, in general, there can be two variables still. Yep. All right. So now let's, same thing as we did before, we're going to set those two equal to each other. So let's use different colors. So this tells us that x is equal to x plus c sub y, comma z. This tells us that c sub y is equal to, whoops, c sub y, let's leave the independent variables in there just to be clear, is 0. So if that is 0, what does that mean about c of yz?
It's a K.
It's a constant.
It's not just a k.
Is it 0?
Not just a k.
Relies on z.
So c of y comma z is really,
Z.
I think I just heard someone say it,
Relying on z.
just on z.
Oh my god.
C's and parentheses are.
Okay, so let's make sure we understand that. So if c,
Just 1 0, right?
if the constant with if the partial of the constant with respect to y, where we have y's and z's in here, is 0, that means there's really no y's in here. If we're partialing with respect to y and we get 0, it means there's no y's. Right?
Yeah.
If there's a y in there, we wouldn't get 0.
We at least
Right?
get one.
If we partial to
Right?
respect
If
to
we
z,
have, if this was what our constant looked like, and we partialed it with respect to y, we get 1. If there's any y's at all in here, we are not going to get 0. We can't get 0. So therefore, the constant the constant up here that has two variables really only has one. So it's constant with just z's and numbers in it. All right, so now our new phi, we are now to the point where phi, so now we're coming over here, we have phi equals xy plus a constant function of z. Now we have to partially differentiate with respect to our last independent variable, partial with respect to z. We get phi sub z equals 0 plus c prime of z. If we partial this with respect to z, and that has only z's in it, then that's really just a derivative. We now have two expressions for phi sub z.
It's 1.
So we set them equal to
So
each
it's
other.
Z.
Set them equal to each other, and it is what you think it is. We get 1 equals c prime of z. Integrate both sides, and we get c of z is equal to z plus k.
No.
So now we've completely recovered phi. Phi, our conclusion is that phi is equal to xy plus z plus k. And if we double check, phi sub x is y, phi sub x is y, phi sub y, did I say that right?
Yep.
Phi sub y is x, phi sub x is y, and phi sub z is 1. So we got back to where we started.
Wow.
I think it's time for a break. just a hunch. Just a hunch.
So if we partialed first instead of with respect to y, we did x and we got zeros, then we would just, like, the x's would go away instead of the y's, right?
So if we started here,
I guess so. I think I'm starting to, like, understand, but I don't want to.
so when you have a partial with respect to x here, we integrate with respect to x.
Okay.
Here, if we started here, we'd integrate with respect to y, and we get xy also.
But that's why you can get rid of your y's and the constant down there, is because when we first partially differentiated right there, we did it with respect to y. So when we got a
Yes.
0, we just have c and c left.
Yes. Yep, that's right. Oh, thank you.
Can I write my name on top of all those?
It'll be fine. I'm gonna seal it right now.
Okay, or staple it.
Seal the deal.
I don't. I'll just seal it and go put it
I know, I was
inside
like,
my.
mine's on the bottom.
Oh, thank you.
I wrote it all pretty.
I can't wait.
I don't have.
Well, I got stuck on one.
Which one?
Number 10. I don't know why I have this number 10.
Oh, you have. Oh, there.
For 10.
Fold that
It's the
on
only
the
problem that's
outside.
stopping you from taking the test. I know it's going to be on there. I don't know how to do it.
We were working on 10 hardcore the other day. Thank you.
Is that a dragon?
That's the reef symbol.
Oh, no, the necklace.
Oh yeah.
Oh, cool.
The exam for changing the
Thank you. Is there any chance I could give you the instructions later today?
Yeah, I figured it out eventually.
Get back.
Thank you.
That would work for me.
Yeah.
Yeah, that'll work for me. Yeah.
I had no idea.
Yeah, you know where my
Do you remember
office
what it
is?
says?
13, 18, right through
It
here.
doesn't really matter.
Just down the hallway?
Yeah, that's good.
I
I'm
know
good.
it's a parabola, so I can just build another one on the top.
Actually, I have enough wires somehow.
There's like a sideways parabola and then
Yeah, so I've got,
plain.
you can either go out there and go through.
Yeah, I could build one.
Is that the one where you're like, was that
Just had to change the order.
Sorry, what?
It was like D, Z, D, X, Y, and then
I don't think there is
Y,
any more
D,
Alex.
X,
Before.
You
Oh.
know,
Yeah.
it's just I
Oh,
couldn't find
for
any
chapter
examples
11?
in here.
Yep.
Is it due today?
Yes.
Yep, and I couldn't find any
It's not very many
examples
topics, so I think it's like
at all on
3
how to do it. And then, like,
or something.
I
Yeah, it's not that bad.
couldn't.
Have you taken the knowledge check though?
Let me take it.
So that, it'll make this that first.
Is there any way that I could like take a picture of one of the problems? Because I want to help her
Yeah,
figure
absolutely.
it out later.
Totally fine.
Okay.
What number? 10?
Oh, 10.
Oh, that'd be great. Yeah, no, I think that's a great idea.
Okay, because then that way we
Yeah,
don't
yeah,
have to
that's
worry
a really
about
important one for you there.
That's usually who I ask.
Yeah.
Okay,
They
cool.
give me random stuff.
Thank you.
That's-
Can I see number 10 too, really fast?
Oh, Professor.
Oh no, we're not. She's just taking a photo of number
No, no,
10, so she
we're
can
gonna-
work on
We're
it.
gonna work it later.
Yeah.
So,
Got number 10.
Yes.
we're gonna work it.
Go.
Oh my god.
If you look on these X direction, what do you see? It's
Half parabola. Yep. Just so in the YZ plane, you get that.
So you look from the x direction.
Yep.
Oh, just the top, just a quarter, right?
Yep.
Yeah. Okay.
I drew it correctly, yay.
And then I have the test corrections, but I wanted to see if I could go over two of the questions with you, like after class.
Yes, definitely.
Okay.
Yeah, I will take it and we'll look right after class.
Okay.
Piece of cake. Sounds good. Sounds like a great idea.
So also
That
related to
does
what
not
you
want to
said,
slide.
I've got a few that I wanted to go over with you too. I have work right after class though, so I won't be able to make it after class today. Is there any other time later this week or maybe on Friday?
Tomorrow, are you on campus tomorrow?
Yeah, I have physics at same time as this class.
We could do it before then. We could do it at noon.
Okay, I can do that.
Noon to 1.
Okay.
All right, my office, noon to 1, 1318.
Is the Math Center
It's a
open
plan.
over the break?
No.
Okay.
Mass Center closed over break.
Okay.
Unless you want to work in there.
I will.
No, they closed the whole Mass Center, Writing Center, all that stuff.
Okay. I know they want me to do something with science.
Over during the break.
So, yeah, we always do something with break.
What?
Whatever they want me to do.
But nothing with students, just like prepping labs
no.
or.
Yeah, like prepping, breaking down. I'll probably go clean out the physics store. Because I know that Chris has been wanting to like organize all the astronomy stuff.
Oh.
So they'll probably have me come out.
Okay. That's kind of cool, actually. That there's something to do.
There's always something to do.
There's always something to do
There's
there.
always something to
There's
do.
always
Over
something to
every
do.
break, I've never not had to work. And you can work 28 hours in the breaks.
Oh, that's great, actually.
So that's what I wanted to do. I was working.
Yeah, this summer we had Valana. She worked in the Mass Center 15 to 20
Did
hours
she?
a week.
I missed her.
Yeah, she did 15 to 20 hours a week.
I had Calc 1 with her over the summer.
And so that would have been the previous summer.
Yeah, it was Calc 1, and then we did Calc 2, and that was the class that I went through.
And then, that's right.
Yep.
That's right. And then, someone else was working with her in the summer. We had another student in there. Javier or Xavier? Xavier.
Oh, Xavier.
Yeah.
He was my lab partner.
Yeah, he was pretty solid.
He always liked letting us struggle too.
Yeah, there's always something to struggle on.
He was supposed to
Oh,
say
I
Calc
don't
3
think
was
it's all right, yeah, don't be looking for that. I don't need any gifts.
I don't need any.
No gifts, please. No beverages. All right, so let's do another triple where we find the potential function. So the potential function of that is going to be found. Well, let's first decide whether we have one or not. Let's do the curl. So curl of the vector field. If it has no curl, it's conservative. No curl.
I have a feeling we're gonna have curl on this one. Actually, I have a feel no curl. Sorry, I feel no curl.
You feel no curl?
No curl.
Feeling it. Feeling it.
Feeling the no curl.
Like it is conservative, Omar?
Yeah, I feel that it is conservative.
Dang it.
I don't think, are any of these going to have curl?
Well, the ones in 3 space definitely are not going to have curl. The ones in 2 space, if they don't have curl, how do you integrate them?
What?
Yellow, just someone.
If you have a curve in 2-dimensional space and it's not a conservative vector field, then you do it directly. You parameterize the curve and you integrate it like we've been doing it.
Oh, okay.
So this is we're leading to a place where this is going to give us a shortcut if it is a conservative field. Okay, so let's partial this thing out. That's a partial. This with respect to y is x. Partial of that with respect to z is x. Partial of that
That's
with
a bad
respect to
sign.
z, that's 0. That's 0. That's okay. Partial of that y minus y. Last one is going to be z minus z. All right, so it is 0. 0. Therefore, conservative. Okay, so that means that we can write phi sub x is equal to yz. Phi sub y we can write as xz, and phi sub z as xy. All right, that's where we're at. Partially integrate the first one. with respect to x, so we get, whoops, let's write our phi in there. So we're going to have phi equals xyz plus constant function of y comma z. Another reason to sort of do it the same way every time, start with the x, is that you get into a pattern of steps that you can recreate again and again and again. Helps if you just do the same process each time. So then we'll partial this with respect to y. Look at that. And this is a good one again. This tells us that c sub y of yz is equal to 0, which tells us that c sub y of yz is really
C sub Z or C of Z.
c sub y of just z. We partially differentiate with respect to y, and we get 0. There's no y's in there, so there's just z's and constants. So we can call it a constant of just z. So then we add that to the phi that we had above. So then phi is equal to xyz plus c sub y of z.
Do we need that sub Y?
Yes. Right? The partial with respect to y of this is 0, which means the partial with respect to y, it's really just a function of one variable, but it's still. Oh, wait.
We didn't do that the last
Yeah,
time.
no. Yeah, I'm sorry. Yeah. What am I saying? What am I saying? This is what I'm saying. That's what I'm saying.
Oh.
Yeah, if the partial derivative with respect to y is 0, it means the original constant didn't have any y's, so the original constant with no subscript is just c of z. Yeah, thank you. Yeah, it's easy to get tangled up in these things. Okay, so that's plus c of z. And then we partially differentiate with respect to z. So phi sub z, which is xy, plus c prime of z. Now we have two representations for that. And we make a conclusion pretty easily. So this all implies that c prime of z is 0, which means c of z is a numerical constant. Numerical or numeric?
Numerical.
Numerical.
So if it wasn't 0, that would just be that
Then we
number?
just integrate it. So like one of the other ones we had c, we ended up with a letter there, and then we would just integrate. So if we ended up with c prime of z is 2z. All right, so therefore our potential function is xyz plus k. xyz.
What about the? Never mind. I'll figure this out eventually.
So the question next is, what do we do with these potential functions? We have a field. It's conservative. We build this phi. What do we do with phi? So, well, we all know about fundamental theorems. And every type of integral has its own fundamental theorem. So now we have a new type of integral called a line integral. It will have its own fundamental theorem. And the fundamental theorem for line integrals is just like the fundamental theorem in Calc 1. The fundamental theorem in Calc 1 said if you integrate a function, you end up with an antiderivative, and all you have to do is take that antiderivative and evaluate at the two endpoints and take the difference, right? That's what our fundamental theorem here will do. We take our potential function, we evaluate it at the endpoints and take the difference. Same exact method. You find an antiderivative, so in our case that's now phi. We evaluate it at the upper endpoint, evaluate it at the lower endpoint, and take the difference. So same as it ever was. Same as it ever was. So fundamental theorem, but it only works if f is conservative. So if f is conservative, we can apply the fundamental theorem of line integrals, because the whole point is to evaluate integrals. We wouldn't want to go through this whole definition of conservative field and potential function if it wasn't helpful for integration. And that's how it's helpful for integration. All right, so let's do it.
Question.
Yeah.
So what do you do if the vector field is not conservative?
Then you integrate directly like we have already been doing. You parameterize your curve, right? You do f dot dr is equal to f times r prime, and then so you integrate directly.
Okay.
So that's a direct evaluation versus the fundamental theorem.
Okay.
Yeah.
Is it assumed then in those first types of problems that we were doing that there was curl? Like we weren't told that?
Some of them would have, some of them would be conservative, some wouldn't. You can always integrate directly.
Okay.
If you can parameterize your curve. You can always do it directly.
Okay.
It's just that we're going to see that if you happen to be in a conservative field, there's some shortcuts.
Okay.
That's what we'll see. But you can always do it directly, which is what we're going to do here a couple of times. So here they say, use the parametric description to evaluate directly, use the fundamental theorem. So we'll do it both ways, just to see that it doesn't really matter. Now, one observation though, if our paths happen to be closed, what should the line integral give us? 0. Just like if you integrate and your start point and end point are the same, if you integrate from a to a, you get 0. Same idea. So this is going to give us a shortcut if we happen to have a closed path that we're integrating on, and we know it's a conservative field, we instantly know that it's 0. So if we integrate on a closed path through a conservative field, we get 0. That's why when you do that whole physics stuff where you're moving an object and you end up back at the same point, there's no net work that's done. Conservation of energy. Okay, so here it says do it directly first. So we've got a curve. It's a circle. So it is closed. So let's see what happens. All right, so integral of f dr on the curve. And bless you. So let's figure. We didn't even figure out our f yet. So capital F is the gradient of this potential function. Oh, this one's so silly. So silly. Okay, so they gave us the potential function, right? They gave it to us already. They gave us the potential function, so we can build our gradient field. The gradient of phi. Isn't it going to be, we partial out with respect to x, don't we just get
X plus y.
We get an x and then a y?
X.
Is that what we get?
Yeah.
Partial with respect to x, the y's go away, we get 2x over 2, so there's our field. So our field, we're going to integrate, do it directly this time. We've parameterized, and this is what all x's are equal to, that's what all y's are equal to. So we're going to write that as sine comma cosine. So this sine comma cosine is the field. Now we have to multiply it by r prime. R prime is cosine comma minus sine. And we parameterize this on the interval. Oh, I thought somebody told me it was a closed path.
It wasn't. We
It's 0 to
decided.
pi.
0 to pi, so it's not a closed path. I'd have to go 0 to 2 pi for it to be a closed path. And that's why I said it was silly, because I believed you. Because if it was a closed path, what would the answer be?
0.
0, right? Because we started with a function, we built this, we know that's a conservative field because we constructed it from a function. So we instantly know it's conservative.
Say that one more time.
So if you start with phi,
You know that.
and you build your gradient of phi, that field's automatically conservative because you built it from a potential function.
Built it.
The more complicated thing is when you get the field and you don't know, is there a phi or not a phi? is there a phi or not a phi? And if you figure out whether the field is conservative or not, then you know whether there's a phi or not a phi.
So just because you have a closed shape does not mean that it's always going to be a closed loop. That's my question. Is that?
So you said is if it's a closed shape?
Yeah. So like, let's say you had like a semicircle that was bounded by like an axis.
Oh.
It'd be a closed shape, but it isn't like a loop that you could.
It's not a closed curve.
Okay.
Right. Yeah. So you can have a concave curve that's not closed.
Or like bounded by something.
Yeah. That's true. Yeah.
Okay.
So in that case, if we did want to form a closed path, like you're describing, if we wanted it to be a closed path, then we would have to have a piecewise defined boundary. So the circle could be, part of the boundary, and then that X segment is the other part.
But just because it would be like bounded by that does not mean that it's a closed loop curve.
Right.
Okay.
Correct.
That's,
It would have to be.
So do we just get
One dumb question allowed.
Okay. So we found our which is x, y.
Yep.
Then our r is literally just the same because our x.
Because it's x comma y.
Okay, and then we take the derivative of that, and that's where the cosine is.
That's
Okay, sorry. I don't
Yep.
know. I was
Nope.
really confused.
Well, we haven't done this for a couple hours.
I'm sorry.
So this is f and this is r prime.
Okay.
And we've been doing all that other stuff, which is easy to forget.
Don't we just get pi?
Pi? What?
Don't we just get pi?
I don't know. Did you already integrate?
Well, you don't need to integrate. Because the dot product is going to just give you 0.
Oh yeah, it does. Gives us 0. So what does that give us total? Pi times 0 is pi?
Well,
Why?
Yeah, 0.
Okay, 0. 0. So sine times cosine and minus sine times cosine. So the integrand is 0, and then we get pi times 0, which is 0. Okay, so you can get 0 on a non-closed path, obviously. All right, and let's see. So let's put a
Wait,
box around that.
can you explain why, like, that makes sense that that's 0? Is there like a way that would make sense?
Let's see, that's a good question. So we've got, our path, the path that we're looking at is just this semicircle. So the question then is there a reason that we can, or why can we interpret that? How can we interpret that? So we have that. So remember that FDR is adding up all the tangential components. So somehow they must be offsetting each other. If we're going to get 0, and we start looking at the FDRs, we're looking at the tangent vectors. The tangent vectors are coming from the derivative. So let's figure out what those look like. That's a great question. So right here, what does the tangent vector look like? So this point right here is 1 comma 0. And what does the tangent vector look like? Okay, so we're at 0. Cosine of 0 is 1. So it's 1 comma 0. Oh, interesting. And it's pointing, that's not quite long enough, it's pointing to the right. No tangent vector. Tangent vector has 0 length. And so what we're going to see if we keep doing this, at every point, the tangent vector, I don't want to say the tangent vector, I want to say the derivative. Is that right? Let's try again. Let's do one more point, just to make sure we're on the right track here. Let's suppose we're right here where we're at root 2 over 2, comma root 2 over 2. So this is pi over 4. Bless you. Cosine of pi over 4 is root 2 over 2. Sine of pi over 4 is minus root 2 over 2. So from this point, we're going to go. That doesn't make sense.
Isn't it because the fact the left and the right are the same, but opposite, so they're just going to cancel out?
That's probably what it is. Because the vector right here, certainly that has 0 in terms of the tangent direction, that derivative.
You got pi, right?
The thing I'm confused about is that when we take let me think about that for a second. That's r prime, and r prime right there should be tangent to the curve. Why is that not tangent to the curve? Plugging in 0, we get 1 comma 0. Why is that not tangent to the curve? Oh, we're not. I was misinterpreting the parameterization. Where are we at t equals 0?
0, 1.
We're not. This is where we're at if the parameterization is cosine comma sine.
We're at sine comma.
We're at sine comma cosine. Like something is very weird here.
So we're at pi over 2.
So that is definitely not, because this should be a tangent vector. That is not a tangent vector. But at first I thought it made sense because, delete. At first I thought it made sense because the tangent component was 0, but that's not. That was for the wrong reason. Okay, so if we go to a point on this curve, pick t equals 0. Where are we at t equals 0?
0, 1.
So t equals 0, we're at 0, 1. So there's t equals 0. Now we apply that tangent vector, and that was 1, 0, so it's going to go over like that. Right? So and so then we're going to, let's plot another one. So at pi over, let's plug in t equals pi over 2. So at pi over 2, sine of pi over 2 is 1. Cosine of pi over 2 is 0, so we're at 1, 0. So we're over here when we're at pi over 2. And the derivative vector at pi over 2 is going to be 0, negative 1. So that's going to go straight down. Okay, so it looks like we're going to get this situation here. And so if we add up all those tangential components, do we see that they balance each other out? Right, this one right here, that's going up, this is going down. This is going to be here, but this is going to be here. So there's going to be all the x's are going to cancel out.
What cancels the top one then?
Yeah.
What cancels that one?
Yeah, I don't see any.
Oh, good point. Let's see. We're adding up. So this x, I'm not sure. Oh, let me think about that. Because what this is saying is that all the tangential components should be adding to 0. So there should be a balance of it. So where is it coming from?
But what is it measuring? Because the slope would be 0 at the top, right?
The slope is 0, but the magnitude of this tangential component is 1.
Isn't it going both ways with that vector though? Like it's going both left and right?
Left and right at that point?
Yeah.
Should only go one direction. I'm wondering if we should double check these over here. I wonder if these are going the opposite direction. Let's check. So we plugged in t equals 0 and t equals pi over 2. What about t equals pi? When we're at t equals pi, sine of pi is 0. So we're at 0,
Negative 1.
0, negative. Oh, that's what it is. We drew the curve wrong too. Right? The semicircle is if we go cosine, sine.
Oh, so it's not even that way.
It's not even the right curve. Yeah.
Okay.
Total fail.
Total fail.
The parameterization matters.
Curve is not to scale.
This is not just this.
Scale out to the proper
No, this is. Yeah.
Get a picture of the
Your question is the perfect question, though. It's this curve.
Oh, that makes so much more sense.
Yeah. So that's where it is. Yeah. Yeah, it seems very odd. Now it makes perfect sense. Now it makes perfect sense.
All right, what cancels
This
the
x
top,
is
right?
negative, this x is positive.
Oh, it is.
This x right here is positive,
Okay.
but then there's going to be a negative x down here. Right, this x here is negative, this x here is positive. There's just as much positive, well, wherever they start, just as much positive x's as negative x's.
They just add up and cancel out, but that one doesn't have a tangential because that one only has perpendicular. And so everything is just...
Yeah, this one has no x component already. Everyone follow that? Did that make sense? Because we're adding up all of the tangential components. So if we look at the x component here, it cancels with the x component there because this x is positive, this x is negative. This x for this one is 0.
How about y? Because it's a vertical line.
No x, just y.
It's a vector that's 0, 1, 0.
So why do we only look at the x?
That's what this line integral does. This line integral adds up all of the tangential components. Well, let's keep going. Let's, yeah.
Why? Will you remind me why that parameterization is just the right half of the circle?
Well, because we agree that it's a half a circle.
Yes.
And then we just plug in 0, and when we plug in 0, we get that point, and when we plugged in pi, we got that point. And when we plugged in pi over 2, we got that point.
So it's just because of the
It's
interval?
just because of the interval. Yeah, yeah. All right. I'll add some extra commentary to that. Let's do a couple more problems though. So let's finish off this one using the other technique. So this technique was using direct integration.
We established that's very convoluted and confusing.
Pardon?
Yeah, we established that it takes about 15 minutes to get to that one.
Yeah. Well, no, it took us no time to get to there, but we were trying to interpret it.
Yeah.
I didn't spend any time thinking about that. It's a good question. You should always ask that question. Should. Just next time do it after class. Okay, so this field is conservative. We know it's conservative because it came from a potential function. So the fundamental theorem says that we should be able to figure out the answer here by doing phi of the upper endpoint, so this is when t is equal to pi, minus phi of the lower endpoint, that's when t is equal to 0. So what we need to do is look at our parameterization and calculate the ordered pair that goes in here. Phi is a function of 2 variables, so we have to plug in an ordered pair. So we're going to say, what is the ordered pair when t is pi? So when t is pi, we go here. When t is pi, we're at 0, -1. So it's phi of 0, -1 minus phi of lower endpoint is 0. Plug in 0 and sine of 0, 0, 1. So we do that. And then, let's see, we still have phi up there. X squared plus y squared over 2. So we probably can squeeze that in. X squared plus y squared over 2. So x squared plus y squared over 2 minus x squared plus y squared over 2, and we get 0. So, which, pardon?
What was that last part you did? X squared plus y. Oh, you just plugged them back.
So the original, the phi is right here, and so what we have to do is figure out the ordered pair on the curve at this point, and the ordered pair on the curve at that t value, and then we do phi of the upper minus phi of the lower. So the ordered pair at pi is this. The ordered pair at 0 is that. So we evaluate phi at the upper minus the lower.
So you did plug them back into x squared plus y squared.
Yep, 0 squared plus 1 squared. Yep. Plugging it back in, plug and chug. All right, let's go to this one. So this says that we have a function of 3 variables. They've parameterized a helix type thing from 0 to pi. Let's figure out ahead of time, since we know we're going to use the fundamental theorem at some point, let's figure out the ordered triple for each of those t values. So let's figure out what r of 0 is. And now this one we can't draw, so that's good. So plugging in t equals 0, sine of 0 is 0. Cosine of 0 is 1, and then 0 divided by pi. So this tells us that our lower endpoint, call it A, is the ordered triple 0, 1, 0. And then we figure out r of pi. R of pi is going to be 0, -1, 1. So the B, the other ordered triple, is that. So we're moving along a path, it looks like a helix, from this point to that point. All right? They've parameterized it for us, so let's do the direct method first. So the integral on the curve of f dr is going to be, bless you, integral of f. Let's calculate our f. F is the vector field that is 1, 1, 1. So that vector field, we put it here. We take the derivative of the parameterization. R prime is going to be cosine, comma, minus sine, comma, 1 over pi. That's what goes in over here. Cosine minus sine 1 over pi. And that's a dt. And we're going to go 0 to pi.
Aren't you missing a 2?
Maybe.
Or with pi?
Let's see. So we're differentiating. This is r prime. Derivative of sine, derivative of cosine, derivative of t over pi. No t's.
Okay.
No t's. Question?
Did you just get your 111 from taking the partial of phi?
So the
Respect to each other.
gradient, this is the gradient of phi. So yes. Partial with respect to x and then y and then z. And this gives us the integral from 0 to pi of cosine minus sine
Is it
plus 1 over pi dt.
Oh, it's plus now.
And then we get sine plus cosine plus t over pi 0 to pi. And what's our final answer? Sine of pi is 0, cosine of pi is -1. -1 plus 1 is 0.
What?
I think we're going to end up with -1. Do we have confirmation of -1? When we plug in pi, sine of pi is 0, cosine of pi is -1 plus 1, so that's 0. Plugging in 0, we get 0 there, and it's minus, so it's -1. Okay. So that is using the direct method with the parametrization that was given. Now let's use the fundamental theorem. So the fundamental theorem says, take your potential function, right there, evaluate it there, and subtract off the evaluation there. So phi of b minus phi of a. And actually, let's probably squeeze it in right here. Let's notice that phi of a is, so phi of point A, plugging in that is 1. And phi of b, when we plug that in, we get 0. So then phi of A minus phi of B. Let's move that over. So phi of A minus phi of B is.
Oh, it's negative.
Oh no, it's phi of B minus phi of A.
Yeah, it's
Phi of
negative.
B minus phi of A. So phi of B minus phi of A equals -1.
It's so much easier.
So we put in A's and B's as opposed to the pi's and the zeros?
So
like
the
last
A's.
time?
Yeah, so well, the A's and the B's are after we figure out the ordered triple from putting in the pi's and the zeros. So that number, of course, is going to match. So if you have a conservative vector field, the fundamental theorem, I mean, that's what we always use when we integrate is the fundamental theorem. Right? That's what we always have been doing, fundamental theorem. So it's going to be easier because it works, so it's such a nice computational method. All right, let's go to, I don't think I skipped the page. Okay. So, some conclusions. When we're looking at a conservative vector field, if we have a closed path and a conservative vector field, we already talked about this, the integral necessarily is 0. If it only depends on the endpoints and the endpoints align, then phi of A minus phi of A has got to be 0. So only if you have a conservative field. Conservative field.
The circle in the integrand, that means closed?
So this new accoutrement means that the path is closed. Usually we interpret it to be a simple closed path oriented counterclockwise. Simple closed path oriented counterclockwise. In practice, you can just think of it as a closed curve. It's going to be a closed loop. It's not going to be self-intersecting. It's going to be a simple closed curve. And typically we orient things counterclockwise, but you don't have to worry about that right now. That just means it's closed.
And
So,
yeah,
closed
with-
path.
Yeah, pretty much that circle there just kind of tells us also that that integral equals 0.
If we know that f is conservative, then that means it has to be 0.
Okay, so pretty much if we see that anywhere in an equation, we just put 0 into that equation
Yeah.
instead.
Yeah, any closed path on a conservative field will integrate to 0. Okay, this typo here, that's really just the curve that's supposed to be down here. I don't know how they didn't catch that, but yeah, that's not there. That's just the curve. So this says that we have another way to think about a conservative vector field is that every single closed path integral is 0. Obviously, that's a bad way to test. You can't test every closed path integral. But that's another way to think about it. Every closed path integral being 0 means the field is conservative. The field being conservative means every closed path integral is 0. Just another way to think about it. All right. So, oh, they did the same typo here. That's weird.
I think they're forgetting to type underscores.
Yeah, I guess so. So for the following vector fields, closed, oriented curves, parameterized C, blah, blah, blah. All right, so circle of radius 8, centered at the origin, oriented counterclockwise. So they're asking us to parameterize C. So what is a parameterization for circle of radius 8, centered at the origin, oriented counterclockwise? Yeah. That's it. That's it. And t will go 0 to 2 pi. So if t goes 0 to 2 pi, that, and you can include this endpoint here. It's a little fishy. When we use the fundamental theorem, we're going to be plugging in 2 pi. Sometimes you'll see this with a parenthesis, sometimes with a bracket, but it doesn't really matter either way. Okay, so that's our parameterization. Now we take the derivative. When in doubt, take the derivative. So there's our derivative. Now we're going to do a direct integration. So we're going to integrate this. FDR on this curve. So we're going to have the integral of f, which is y comma x. Y and x are determined by our parameterization that we chose. So we're going to have 8 sine of t, comma 8 cosine of t, dotted with the derivative. So dotted with minus 8 sine of t, comma 8 cosine of t, dt. This is 0 to 2 pi. All right. What's that? Minus 16 or no? What is it? Maybe not simplifiable.
64 sine.
So it looks like we have negative 64 sine squared plus 64 cosine squared. dt.
Is that a identity or something?
We have a cosine of 2t identity we could use.
Yeah,
that might make this easier. Otherwise, we'd power reduce it.
Did you drop a pi in there?
Dropped a 2.
Yeah. Add a pi.
Add a pi. Pi plus pi. So we could use a double angle identity. We could power reduce it. Lots of. Doesn't really matter. Let's just power reduce it this time. Power reduce. So we know that sine squared is 1/2 minus 1/2 cosine of 2t. So this is going to be minus 32 minus 32 plus 32 cosine of 2t. And then this one is going to be plus 32 plus 32 cosine of 2t.
So that's 64 cosine 2t.
Mm-hmm. And 0 there. So when we integrate,
Couldn't you rearrange it as 64 cosine squared minus 64 sine squared? And that's cosine 2t?
yeah, we could, that,
Okay.
yeah, that's what we said. We could do it that way or power reduce it. I said let's just power reduce it this time.
Okay.
Yeah, either way, totally fine. So then we get 64, and we integrate that. We get 32 sine of 2t. How unsatisfying.
I honestly hate getting 0.
0.
0 makes me feel
Zero.
like I did work for nothing.
I know.
There's so many times when zero's not an okay answer, though. You
Yeah.
actually get 0 and it's fine. I'm like, what?
It doesn't feel right. See? Well, I think they asked us to interpret that.
Oh, no, let's not.
So, C is the circle radius in theory. Okay. If the integral is not 0, give an explanation. I think we should give an explanation even though it is 0. Is it by coincidence or do we have a conservative field?
Conservative.
Conservative field, everyone agree? To determine if it's a conservative field or not, we would do the first, this one, which we're going to call little f, this one little g. We're going to do f sub y, which is 1, and that's equal to g sub x. So f is conservative. So we just verified what we thought we should get. We should get 0 because it's a conservative field on a closed path. All right.
So technically, we didn't even have to do any of that.
Because we knew it was conservative. We knew it was a closed path.
We could have.
Question.
Yeah.
So if you give us the function like on a test and you ask
Function
us,
or field?
If you give us a field on a test and you ask us to evaluate the integral and figure that out, couldn't we just take the partials? If it comes out as 0, don't we not have to do the integral because we know that it'll be 0?
If it's a closed path, yeah.
Okay, so we could have gotten out of doing the integral there if we just done the partials first. Okay.
Yep.
It's not going to give us anything that easy.
That's right. So we didn't test that it was conservative ahead of time. So what they wanted us to do was evaluate it, and if it wasn't 0, then we would conclude that it's not a conservative field. Now, just because you get 0 doesn't mean that it's a conservative field.
Right.
You can get 0 on a closed path for a field that's not conservative. But if it is conservative, you know you're going to get 0.
For
All right.
all of these, just test if it's conservative first.
That's yeah. It's a closed path. That's a good idea. Okay, so I think this one has the same instructions. Should we test to see if this is a conservative field?
Yes. Yes.
Let's test. Okay, so conservative field, we have to find the curl. So if it's a conservative field, the curl will be 0. Do we have a closed path?
Yes.
Do we?
I think so.
Let's see. So A, the first point, if we plug in 0, we're going to have 1, 0, 1. And the second point, we're going to have 2 pi cosine of 2 pi is 1. Sine of 2 pi is 0. Cosine of 2 pi is 1. Yeah, so we have a closed path. Bless you. So if this is a conservative field, we instantly know that the integral is 0. So let's see. It probably won't be a conservative field. All right. Watch.
It'd be the first one
Yeah, exactly.
that's not a conservative field.
All right, -1. What do you get for that first answer? -2.
Dang it!
Really, you need to keep going. It's not conservative.
Okay.
Right?
Is that just a test?
Instantly. We know it's not a conservative field.
Right.
So the only way to integrate this is through direct integration. It's not a conservative field. No shortcuts.
Parameterized it. Well, it's parameterized already.
Short.
They all need to be 0.
Oh, that would matter. Like it was, it's going to be y minus c.
So the AD just tells us that we start and stop at the same point. So that tells us if it was conservative, then the integral would be 0.
the middle term is gonna go away, right? We
But,
did it directly.
so let's figure out this integral. We're going to integrate from 0 to 2 pi.
How did you get -2?
So partially, this with respect to y is -1. And then subtract off the partial of that with respect to z. So it's -1 minus 1.
Right. That's how you do that.
Yeah, that's how you do that. All right, so let's do some dot producting. So y minus z, we have sine minus cosine. I'm going to use shortcuts here, I think. I'm just going to use s and c. So sine minus cosine. Sine minus cosine. And then z minus x, 0. And then x minus y is cosine minus sine. And that gets dotted with r prime, so minus sine, comma cosine, comma minus sine, dt from 0 to 2 pi. Dot those together. And we get minus sine squared plus sine cosine plus 0, and then minus sine cosine plus sine squared dt, and that's all 0. Right?
Here.
Yeah.
Just goes away.
Just goes away. All right, so that is 0 by coincidence, not because we have a conservative field. So sometimes closed path integrals will be 0. Randomly. Randomly. All right, cool. Next one. So evaluate each line integral using a method of your choice. All right, go for it. You guys evaluate using a method of your choice. You have two choices. Fundamental theorem of line integrals or directly.
Where the hell does gradient come from?
What's that?
Gradient.
What about it?
What?
You want me to do that for you?
No, just what does it mean?
What does the gradient mean?
Well,
Is that the gradient of a function?
That's the gradient of this.
oh. Because that makes so much more sense.
I can do that step. So the gradient of this is the vector of partial derivatives. So we have 2x y, z. Partial with respect to y is x squared z. Why am I doing this?
So they're just essentially being dicks and telling us, oh, instead of putting f, here's gradient of here's gradient of phi.
Back to the field, you animal. Yeah. So but the point that they're trying to make is that the field is coming from a function, which means you have a conservative field instantaneously. So you don't even need to find the field.
So they're actually being nice, is what you're trying to say.
Yes.
Okay.
Because it's a conservative field by construction, we don't even need the field. We can just use the fundamental theorem of line integrals and take phi and evaluate it at the two endpoints and take the difference.
Okay, secondary question, this may be stupid. Is there no cussing rule in this class that I did not know about? Because everybody goes, whoa!
Yeah. Usually, have you read the student code of conduct?
Yes.
You read it? How many of you have read the student code of conduct? Oh wow, not too many of you.
Might have, I probably forgot it though.
Yeah. But usually there's a general assumption that we use the King's English.
Keep in mind, you're going on YouTube.
Yeah, you have to move this out.
Hey, boss, I'm a king and I cuss. What are you talking about?
What? You're not even old enough to swear.
If we just
Makes
sense.
Right, because
16-year-olds
but
are
you'd be
I'm 16.
What? You're 17 already?
into there and then
Wow.
And
We're
then
so old.
You're so old. I know, that's crazy. 17. I remember when you guys were all 16. Weren't you 15 when you started here?
I was 14.
I was
started at
too.
Front Range.
14 also?
Yeah.
I remember working in the lab, and you guys were like this tall.
Babies. Tiny babies.
Look at you guys all grown up.
It's fine. It's fine.
All right, so what's the answer?
Nothing.
Oh man, we
Oh,
got that
hold
fast. Whoa. Alright, you gotta plug them in, right? Or
Yes.
take the derivative and dot it.
Well, so if you want to do it the long way,
Okay, I don't.
which will work,
Wait, never mind.
but the
Wait, hold
shortcut,
on.
remember, this field that we're building, we know it's a conservative field because we just built it from a function. And
Oh, that's phi.
So that's phi right there. So we can do phi of,
0 and 5
Yes.
pi over 4.
so all we have to do is that.
You literally
Because we know by construction that that's a conservative field, so we can just use phi at the endpoints and take the difference.
But would that way work that we just said?
Yes.
Same. So you just plug in pi.
So phi is a function of 3 variables, so we need to know the ordered triples. So this is a little bit, that notation's not totally correct. We plug in the 4 pi up here to get the ordered triple. Right? Plug in the 0 to get the ordered triple. So cosine of 8 pi is 1. Sine of 8 pi is 0. And then 4 pi minus phi at 0. And at 0, we're at 1, 0, 0. So those are the 2 ordered pairs. Ordered triples.
And you plug that into that function up there?
We plug it, right into phi.
Okay.
And then you multiply by r.
Then we're done!
That's it? There's no r primus?
No.
No.
Not if it's a conservative field. If it's a conservative field, the fundamental theorem of line integrals just says take phi, evaluate it at the 2 endpoints, and take the difference.
Isn't it?
I don't know. I didn't test yet.
Oh, no, it's not. Because those
No, those
the
are different.
same.
It's not a closed curve.
But it's
Andrew?
still 0.
Oh, no, I was dumb. I remember. I realized we built the field.
Built the field from phi, so we know that by construction the field is conservative, so we just go to phi and take the difference at the endpoints. So what do we end up with here?
Then that means it's 0, so it's just 1 minus 1, it's 0.
Do we get 0?
We get 0, yeah.
Oh, we
We
get
just
0
literally
again?
plugged in 1 for
Oh,
x,
brother.
0 for y, and 4 pi for z.
Okay, so when we plug in 1, 0, 0, we get 1.
One of them for each one. then it's
When we
just
plug
minus
in 1, 0, oh yeah. 1 minus 1.
Wait, so are you...
So the ordered triple gets plugged in for the x, y, z, and phi.
So then this whole little blue stuff that I made you write
Yeah.
is pointless?
Yes! Exactly!
But if it wasn't conservative, it wouldn't be.
But if it was not a conservative field, then we would have to go down this road, but because they said del phi, we know it's conservative. By construction.
So anytime we see del of phi,
Then we can use the fundamental theorem. Even if it's not a closed path.
This is the last
Okay.
one.
Perfect timing.
We're gonna make it
Yeah.
through. Okay.
5
So,
minutes.
oh wow, and this is it. Don't we have a break? Fall break? Fall break?
Oh my god.
Perfect opportunity to get caught up. Perfect opportunity to finish chapter 14's homework. Okay, so find the work required to move an object. So this is just a fancy way of doing what we've been doing. Find the integral of FDR. So a work
It's
integral.
not a closed curve.
Work integral. This is work. Yeah, not a closed curve. So let's calculate and see if this is a conservative field or not. So to consider,
It is.
so we do f sub y, which is 0, which is equal to g sub x. So therefore, f is conservative. So that means that we can use the fundamental theorem. We can take phi of 3 comma negative 6 and subtract off phi of 1 comma 1. Yep.
If it was like 2x comma y, would you apply that when you're plugging
So if
it in?
it's 2x comma y, then we'd say it's not conservative, so we'd have to parameterize the line segment.
Oh, we don't have.
We don't have to parameterize the line segment, but we do have to find phi.
Yeah.
So let's find phi. Let's find phi. That's an easy one though. Phi sub x, phi sub y. So first we're going to integrate with respect to x, and we get integrate with respect to x, x squared over 2, plus constant function of y. Then we partially differentiate with respect to y. So we get phi sub y, that's c prime of y.
Yeah, they're all
So this tells us that c prime of y is equal to y, which tells us c of y is equal to y squared over 2 plus a numerical constant.
Hey, we got our first variable.
Second,
Why is it y squared over 2?
we had one other one where it was not 0.
Oh, it was the very first one, wasn't it?
Yeah, exactly. It was long ago. So there, we've now constructed our phi function. And now we just have to evaluate the phi function at our 2 endpoints. So that will give us.
Do you assume the k is
Assume the k is 0. Why not? So then we get 9 halves plus 36 halves minus 1. Right? Is that it?
Yeah.
Minus 1.
So you just
So 17.
assume the k is
Is it 43 halves? That doesn't seem right, but it might be.
Yeah, 43 halves.
43 halves. 43 halves? C.
Hey,
I
time
see.
for a long break.
All right. Time to stop. It's an interesting class. All right, so definitely finish off reading chapter 14 because it's going to get way theoretical the last few sections.
Way theoretical.
Read ahead. Read ahead.
like, what is that?
Read exactly. Read ahead.